paper. The paper for today is how much do language models memorize? And why is this important? When we look at language models, they have giant parameter count. When you have such a huge parameter count, as we know, for all machine learning models, there is a tendency to overfit or to just memorize the data. And then you also know that they learn something, they generalize from the data. And the whole point of learning is to be able to generalize from the data, not to memorize the data itself, the training data itself. So the question that this paper asks is, how much do language models actually memorize? And the answer, amazingly, is given in very clear terms. It makes a statement that in the GPT family, that is the dominant family out of which large language models or LLMs or chat models are built, you can put a precise number, which is approximately 3.6 bits of memorization per parameter. Now, to get really to the depths of this paper, it's worth talking about a few concepts. One is called double dip. The other is called rocking. And I will set the context for this paper by talking about both of these concepts and what they are. What these concepts are. So just to give you an idea, just to recap what double dip is. Double dip refers to an interesting phenomenon, double dip phenomenon, which is unique to, or which is considered unique to deep neural networks. Considered unique to deep neural networks. But recently there have been studies and researchers are claiming that it is actually not necessarily a property of deep neural networks, but of all statistical models. But nevertheless, commonly we believe that it is specific to deep neural networks, for sure. So what it means is that, see, if you look at the loss function, the test loss, of the model, and you look at the number of parameters or how complex the model is, which is the proxy for model complexity. Then what you observe, as we know, is that you will observe that in the beginning, you will have the model with very high loss because it is too biased. It is the bias loss. But after a little while, it reaches a minimum. And then if you keep on increasing the number of parameters in the model, then the variance loss starts increasing. Right? So because the loss is made up of two terms, the bias loss, let's put it this way, the bias loss, the bias errors, and then it is also comprised of the variance errors. So let's pick another color. Maybe the variance errors, which is overfitting, fitting, or variance errors. And so the cumulative error, which is the sum of these two, this error, in classic machine learning, we expect it to go like this. Now, what deep neural networks show is some very interesting behavior, which is that at a certain point of model complexity, at a certain point, something very interesting takes place. This begins to take another dip, unexpected dip, as you make the model more and more complex, instead of variance errors increasing, you would imagine that it would practically memorize the data. What happens actually is, if you keep on training the model on the data, it actually simplifies. You have a point of double dip. This is the point of, you say, double dip. Because this is your first dip, this is the expected dip. This is the minimum, but then you start noticing that you have this other decline in the total loss. This is the loss here. Right? So this is the concept of double dip phenomenon that you observe, especially in deep neural networks. It came as a surprise to people, and people have different theories on why it happens. Initially, we thought it's only true for deep neural networks. Now, recently, there has been claim that actually it's a property of all machine learning algorithms, right, potentially. But I'm not quite privy on how that statement has been made, but I've heard that statement. But I'll limit myself to deep neural networks for the time being. So this is it. A somewhat related concept is the concept of grokking. So grokking is, let's take the concept of grokking. Grokking is an interesting concept. Again, quite unexpected. What was discovered, actually, this is still thick. What was discovered is that if you again look at the loss, but the x-axis this time is not the number of parameters, but the number of steps of model training. So how long you continue to train the model on the same data set, epoch after epoch, step after step. And what we find is that you have a very characteristic situation like this. As you train the model, the loss plateaus. So this is called the first plateau, the expected plateau. So far, it is exactly what you would expect. The model saturates and says, okay, it seems it has learned everything that it had to learn. Now, and this is the training loss, and so this is at this particular moment you're looking at the test loss. Test loss. Right? Training loss will of course keep on decreasing, and then something very interesting happens. There is a point at which it suddenly goes through a transition. This is called the grokking phase. Let me mark it. A grokking phase. Phase transition. Big grokking phase transition. After which loss now plateaus at a much, much lower level. Right? Much lower plateau. Much lower plateau. And this was sort of most unexpected. Now, there are various theories on why grokking takes place, or what explains grokking. So it has remained part of a research area, though we have a better and better understanding of it. Now, our current understanding, which this research paper confirms, is that in this region, which I will call this region or this realm, regime, excuse me. In this regime of model training, what is happening is the machine is memorizing. Machine or model is memorizing the data, the training data. When you memorize the training data, as you can imagine, that there's only so much memorization you can do. After that, you have memorized the whole training data. It looks pretty good. But your test loss is not going to improve because it has not learned to generalize. It has not learned it. It has just memorized the data. If you take a sufficiently complex model with lots of parameters, it would have memorized. At some point, what happens is that it realizes that it needs to actually learn from the data. As you keep doing it over and over and over again, it gets a hang of data. So you can think of it as a moment of insight. In some sense, at which it begins to understand the data and generalize from it. So this is the beginning of generalization. So just to distinguish the two, to memorize is, for example, to just literally, if you have, for example, if you have lots of images of cows and ducks, it can quite literally memorize each of the images of cows and ducks. And if it sees exactly that image, that photo of cow, it will say cow. And if it sees exactly that photo of duck, it would say duck. But if it saw any other picture of cow, it wouldn't know what it is. So it hasn't generalized from specific instances of cow to the concept of a cow that would help it recognize a cow in a mood. So that is memorization regime. And then you have the generalization begins. And when it generalizes, you know that you have now ended up with a far better model. And so this is grokking. Now, one question that comes up is, at what point does grokking take place? Right? Yeah.
I just have one question. I think with both of the concepts that you explained, it's evident that at one particular point, loss starts dropping again.
That is right, yes.
I wanted to know if for the same model, if we plot both of them, would these points coincide, be in the same region?
Right. In fact, that is specifically what this paper answers.
Oh, okay.
So yeah. So till now, there were two different phenomena, double dip and grokking. And people have always felt that these are related, and there's mounting evidence that they're interrelated concepts. But the thing is, what is the relationship? And one of the lovely things that this paper does is it shows yet another piece of evidence that shows how do these models, especially language models, how do they behave? So with these two things as perspective, there is a final concept that it introduces, which is the capacity, memorization capacity, total capacity to memorize. It's like, for example, how many words can we memorize, right? Or what sequences, how much data sequences can be completely memorized. That is the model capacity. And with these three concepts, let us now read this paper, which is a very, very interesting paper. So let me just summarize the big takeaways from this paper. What it shows, first of all, it redefines. There has been a big problem in the industry. How do you tell whether a machine is memorized something or it has actually learned about that? And an example that it will give in the paper as we make progress is, it says, what is 2 to the power 10? Suppose in the training data, there was 2 to the power 10, and the answer to that is blah. And the machine is able to reproduce that answer blah, right? Which is a long string of numbers. Do you therefore conclude that the machine has memorized it and therefore is now successfully able to regurgitate the answer just because it was there in the training data? Prior researchers have taken the position that, well, look, we gave this as a training data and it has been able to regurgitate it. Therefore, this is clear evidence of memorization. And what these researchers point out is that that's not necessarily so, because the machine could have actually learned how to compute 2 to the power 10, right? And because it has generalized what powers of 2 mean, it has understood that. Therefore, it can do 2 to the power 10 to the power 11, whatever it is. And therefore, it could have produced the answer from its understanding of arithmetic rather than from memorizing specific answers. Another example that they give is, suppose you say addition of 2 numbers. The fact that it can add 2 numbers may be because it happens to have seen exactly those 2 numbers and have memorized their sum, but it could also mean that the language model has learned to sum numbers, do basic arithmetic. And of course, we know that language models do have a capacity to do basic arithmetic. So it is not so clear that uh, that just because it could regurgitate an answer, it necessarily means that it had memorized the answer. It could have produced the answer from generalization. Likewise, if you have a piece of text and if it can produce the continuation of that text, if you give a prefix text and it produces the rest, gives the rest of the text, one could argue that, well, that's a clear evidence that it's memorized the text. But one can counter argue and say, well, and that could be the most probable continuation of the text too. If you really understand the language, then that continuation could easily have been the most probable continuation. And therefore, it is not necessarily an evidence that it has memorized. And so that brings up a very deep question. How, therefore, do you quantify memorization? What is the concrete evidence of memorization? And how do you measure memorization? And how do you measure generalization? Now, when you talk of memorization and generalization, you can talk in terms of statistical terms, information theoretic terms, like Shannon information theory, which would talk about aggregate statistical measures. What proportion of the data? Suppose you have a data set X, right, which is a big data, capital X, and of that data set, let's say that you have a data set X, right? And you have Xi is sampled from X, right? You could ask what proportion of data has it memorized, and the remaining proportion, I suppose, it has not memorized. So if it is able to produce, you can say it may be the result of generalization, right, if it can successfully emit it out. So that remains a question, and you can answer it in proportions of the whole data set, aggregate what proportion it is. But these people take a more nuanced measure coming from Kolmogorov information theory. Kolmogorov was obviously a great mathematician, uh, and his information theory they use, which is based on complexity theory and so forth, and they say, okay, let's talk at the level of one instance of data, one particular data. And the way they define it is that they define memorization. And I'm going to be deliberately vague here because it talks in terms of mutual information and and so forth. Basically, there are two concepts. First of all, let us say that um, you have two facts, X and Y, and there is some amount of sharing of information. Now, the total information of X is this, we can say. But suppose you knew that Y is there. Then what is the residual extra information in X, given that Y is there, right? So that's a mutual information or the residual information and so forth. So there are all of these information theoretic constructs people use, and the concept of entropy, the total information of X is measured as entropy in the Shannon way. And in Kolmogorov information theory, it's measured in a slightly different way as the minimum and a minimum string that can encode a bit of information. You say that the information content of a given data point xi is the shortest representation in bits that can still fully represent xi. Are we together? So they use this concept. So it gets very academic and theoretical, but and they use all of this, and then they tie it back to likelihood, negative log likelihood, and so forth. And so the math gets a little bit involved here. So we will go through some of the math, but not perhaps not in as much detail, because that will take us quite some time. Suffice is to say that the key contribution of the math here is that it comes up with a unique way of quantifying two things. How much has a model for a given bit of information? How much has it learned to memorize? How much is the memorization of the data? And how much is the generalization from the data, the actual learning from the data? Are we together? So when you say that this model has learned from this data, it will always be partially memorization, partially generalization. You would want more generalization to be there broadly, more true learning to be there. And now the whole question is, what is the relationship between these two proportions, memorization versus true learning, which is generalization? And they have a mathematical expression coming from Kolmogorov's information theory, complexity theory, to be able to tell that. And there are certain nuances. Like, for example, Kolmogorov's formulation of it is, in theoretical sense, non-computable. Right? But nevertheless, they use a practical approximation of proxy, and they are able to make head and tail out of it. So that gets into the technical details of it. But we will just assume that these things are measured. So that will help us sort of leapfrog over the mathematics for a bit. But this paper is nevertheless very easy to understand once you take it when you stipulate to the fact that there is a reliable mathematical way to quantify these two things. And then let's look at it. So what we will do is we'll first study the paper without the math, and then in the second iteration, we'll come back and try to see. Now, for those of you who are still interested in the academics, the math of it, we'll then in the second iteration come back and look at some of the math. Right? So that's a plan of attacking or grasping this paper. So with that, let us read this paper. It says, we propose a new method for estimating how much a model knows about a data point and uses it to measure the capacity of modern language models. Right? They don't use the word large language models, but pretty much it's LLM that they are talking about because they are all GPT derived. Now, capacity to know is what they're saying. We formally separate memorization into two components: unintended memorization, the information a model contains about a specific data set, and generalization, the information a model contains about the true generation process. So one way to say it is that, see, whenever, and again, which is a little mathy, suppose you have data X. Data X will inherently have an inherent probability distribution, right? It will have some prior probability distribution on the data, isn't it? And so you could either have memorized the data itself, or you could have learned the real nature of the data. Therefore, that's a generalization or a generalization of the data. Right? So they say by eliminating generalization, we can compute the total memorization of a given model. So they're saying if you just exclude that, of course, which provides an estimate of model capacity, our measurements estimate that models in the GPT family has an approximate capacity of 3.6 bits per parameter. So it says that which the capacity to memorize is only that much. Now, what is the practical consequence? Suppose a machine can memorize, to use very colloquial words, let us say 10 sentences. That's all it can memorize. So you would agree that if you give it 100 sentences, there is no way it can memorize all 100 sentences because your bucket is full. Your memorization capacity is exceeded. So it turns out that this paper shows that only when a machine's memorization capacity is exceeded, that the machine strives towards generalization. Right? In the beginning, it takes the lazy approach. It just sort of memorizes the data to quite some extent. It does generalize a little bit, but initial efforts are towards memorization. And then once its capacity is exceeded, then it generalizes. So they say, we train language models on data sets of increasing size and observe that models memorize until the capacity fills, at which grokking begins. And unintended memorization decreases as model begins to generalize. Now, many of you remember we covered a paper a few months ago on the phases of grokking, which is what I was referring to in this diagram, in which also we said that there is a point at which of training at which the machine starts aggressively transitioning from memorization to uh, true generalization or true grokking. And this paper sheds more light on it. They said very explicitly, they observed that the models memorize until their capacity fills. They can't memorize anymore. At which point grokking begins and unintended memorization decreases as model begins to generalize. Means once you see the pattern, there is no reason to remember, isn't it? And as we did the paper many months ago, in which we saw that the machine was actually aggressively trying to forget. And this is along those lines. We train hundreds of transformer language models, and this is an interesting thing. Models ranging from 500K, 500K, if you put it this way, is 10 to the power 5 parameters, all the way to 10 to the 9 parameters. So you see, we are going across a pretty 4 orders of magnitude, right? From tiny models today, a language model which is only 500,000 parameters would be considered puny, right? To 1.5 billion parameters. Now you might say, well, 1.5 billion is also considered tiny. But this research paper was done on a single GPU. The entire research, apparently, they did it on a single GPU just to standardize and make sure that we have a very good apples to apples comparison, right, on one environment. So they went only up to 1.5 billion parameters. And they produced a series of scaling laws relating model capacity and data size to membership inference. And this is interesting. They come up with a series of scaling laws, and you will see. So what are scaling laws? Scaling laws relate how some feature about language model, they compute, they get some characteristic responds to the size of something else. Right? The size of data, the size of number of steps of training, the size of the model parameter. So some characteristic of the model will depend in a clear relationship, a scaling law, with either some computational parameter or the model's size or the steps or data set size or something like that, right? Some size parameter. So let's see. This is best illustrated even before they get into the introduction. Right below the abstract is a thing. And then they say, and the data size and to membership inference. So this word membership inference is something, a word noting what is membership inference. Suppose I give a model a piece of data xi, and I ask it only one question. Have you seen this data? Was this data present in the training data? Right? It can answer yes or no, or it can answer a certain probability that it has seen the data, more likely. And therefore, you can test. So a model that gets it always right. If it has seen the data, it says I've seen the data. If it has not seen the data, it says I've not seen the data. It means it has perfect recall, perfect memorization. On the other hand, if it is right only 50% of the time, that is the luck of the draw, right? It is just guessing. Means it is not able to do membership inference. At that moment, it has genuinely no recollection whether it has seen the data or not. Right? So that's how the membership inference. The membership inference is, again, you just ask, have you seen this data? And an easy way to do it is if you train with the training set T and you have a test set, what you can do is you can just go through some training examples and some text examples and see, well, have you seen this data? Uh, so membership tests used to be a factor that people considered. But okay, we will study this paper because we have a limited amount of time. We'll study the paper through its charts. The diagrams are very illustrative. Though I must say that as I read the paper, a couple of diagrams I really could not quite understand. So if somebody in the audience understood it better, you could enlighten me. You can enlighten all of us. But I'll explain the diagrams that I understood. The first figure says unintended memorization of uniform random data. So random data is you just give it a random sequence of words. right? If it is a random sequence of words, you realize that there is no way that the machine can generalize. If it can reproduce a word salad, right? The only conclusion you're left with is it must have memorized, because there's no pattern to that word salad. Right? So they are looking at this and they're saying unintended memorization of uniform memorization plateaus at the empirical capacity limit of different. So what happens is, let's look at any one of these models. Let's look at the yellow line. The yellow line represents one particular model, which is about 7 billion parameters. You realize that memorization saturates at about 10 to the 7 bits, right? 10 to the 7 bits is about 10 million bits, right? So it seems to be able to memorize no more than 10 to the 7 bits. So 10 to the 7 is 10 million divided by a model that is 7 million, that is approximately 3.6.
The number for parameter.
That is the number. So it's about 3.3, 3.5, whatever it is. 3.5, whatever it is, 3.5. So basically it's claiming that, or approximately 3.6 bits for all of them, 3.5 or 3.6 more or less, between 3.4 to 3.8, I suppose, is the amount of bits that it's the total capacity for it to memorize. Again, what are the parameters? When you say 7 million parameters, those are your weights and biases and whatnot, all the learnable parameters in the language model. So that is a key finding. And you notice that it's a pretty clear-cut scaling law. Despite the size, you could take a tiny model, only 170,000 parameter model, that also asymptotes. You notice that at this point, they all fly off at this point. Right? When they reach their capacity limit, they begin to asymptote. Right? So that is a key finding. That's the first scaling law that they discovered. The second thing they discover is that as you increase the training set size, unintended memorization not only saturates at a certain point, but what happens when you keep on training it, more and more and more training data you keep bringing in.
It's just taking longer to memorize.
That is right. But more importantly, you notice that as you bring in more data set, it sort of, no, it is unmemorizing it. You notice that for any given model, let's look at this. When you bring in data, which is far bigger than 3. See, this is a training set size 10 to the 6, 10 to the 6 number of data points, and unintended memorization, right? Number of bits that it memorizes begins to decrease, ultimately down to, again, the same value, very low values, right? So there's a lot that it talks about in this paper, but this is interesting. This refers to the double dip, data set to capacity ratio, right? So now, see, if it has a capacity, what would be the capacity? The model size times 3.6, approximately, right? So if you take the data set to capacity ratio, when the data set is much, much bigger, or it begins to reach, look at this point. When the data set is exactly what the capacity of the model is, means the ratio is 1:1. At that particular moment, what happens? The test loss is maximum. Why? Because the model hasn't learned anything at all, isn't it? It has just memorized. But right at that moment, what happens right after that? It begins to start grokking. You have a double dip, right? It begins to, it is forced to grok into the data. And so you have the double dip. You see the double dip. So obviously, implicit here is that we are at this point of the curve. Like this is the part that we are focusing on here in this particular diagram, except that It is not the expected number of parameters, but it's measured by a different ratio, data set to capacity ratio. Right? They're giving it to you.
Can you explain what data set to capacity ratios means?
So suppose a model is 1 million parameter, right? So if you look at this capacity, it will be about 3.6 million bits. Now, suppose you bring in exactly 3.6 million bits.
So it's 1:1.
Yeah, 1:1. That is 10 to the power 1, 10 to the power 0, 1. This is the ratio, data, and this is the capacity. Capacity.
And data would be the number of
The total size of the data, bits of
size
the
of
data,
the data.
in bits, yeah.
Okay.
So what
Size
happens is
versus
when the size is
data
exactly the size, say data set size is exactly as much as the machine can memorize.
then it's always going to be memorize.
Yeah, so far it has just memorized because it's just capable of that. Exactly. So you look at the test loss, it achieves a maximum, which is pretty much what the double dip phenomenon was, right? When your model is very flexible, the machine continues to just memorize it. Right? And when it memorizes it, this is what happens. This is pretty much what you're seeing in a different form. What happens beyond that, when you bring in more data than its capacity, then you literally see that the machine cannot memorize it. So it is forced to do, the idea is, one would imagine that this is forcing it to grok the data, right? Grok patterns in the data. And so you see a rapid decline in test loss. It's actually learning after that. That is the point that is making. Likewise, if you look at the second figure here, train and test loss of different models and data set sizes. See what happens with a training loss. As you bring more and more data points, right? It is able to memorize the data. But as soon as you hit the capacity of the model, it is not able to memorize the data so much, right? So it is like its loss begins to increase. But what happens to the test loss? You see that the test loss is showing a rapid decline, right? Because it is going through the grokking phenomenon. It is the grokking that you are taking and the double descent that you are seeing because of the grokking take place, right? So you can literally see that there was a low here, then it went up, and then it again comes down in the test loss. So that is the real thing that they're trying to show. Another thing to iterate the point that they show is the total memorization. This just says, what is the memorization capacity of a model? So they deliberately take a model which is 6.86 million parameters.
3 point.
Right. So if you multiply it by 3.6, you get a number 23.9. Right. And what you notice is that as the training progresses, it goes in the beginning, all it is doing is memorizing. So the maximum that it can memorize is in 100 steps, a couple of 100 steps is the total amount. You see that this is the asymptote here. So no matter what your training size is, at the end of it, the limits of memorization is this. Of course, if you continue way beyond this, you should probably see a decrease. And the same point they're making out here, total memorization in bits. So they're making the same point, they're reaffirming the same discovery over and over again, just to show that it's a pretty robust finding. And it is true for various scales of the data. You see that how many digits there are? 1, 2, 3, 6. So 8.3 million points of data, right? And here it is only 65,000 instances of the data. So you're going across various scales of the data set size. At the same time, various sizes of the model. And in each of these cases, they seem to come back to this number again and again, which is that these models, their memorization capacity is about 3.6 bits per parameter. Right? So the total memorization in bits and the model size, you can literally see how much they are memorized and the model size. It's a practically linear relationship, isn't it? Practically linear relationship with a slope of 3.6. right? And it's surprising that these are logarithmic scales. These are, as you can see, orders of magnitude scale across various orders of magnitude. This law remains true. Right? That is the main finding in this paper. Now, they do mention the fact that uh, that you know separation from generalization. It is important to remember that what is generalization and what is memorization. You have to be a little bit careful. And obviously, a simplistic notion may not be quite correct. And this is the example they take. Suppose you give a question, what is 2 to the power 10? And this is the answer. And let's say it was in the training data. Can you therefore assume that if it produced the answer, it came from memorization? And what they are saying is that's not so simple because it might have learned to generalize. It might have learned to actually do the math, right? And so you need a bit more sophisticated and mathematically sound measure of memorization and measure of generalization. And which is the key contribution? The key contribution of the paper is that, see, as a warm up, they say there's a statistical view of memorization, which is using mutual information. MI is basically saying that suppose it's a very basic thing. So let me get through this a little bit. I won't go through all of it, but I'll give a flavor of it. Let us say that you have a random variable x, which has a certain distribution, right? Data. So you can say that the information that is inherent in that, you measure using entropy, is the amount of information present in that data set x. Now, if you have two different random variables, x and y, right? And in statistics, you often talk of random variables, even when you know that y might be somehow related to x and so on and so forth, right? So then you realize that there is a certain information in x and there's a certain information in y. But suppose you know y, right? So one example I could give is at a given day, the temperature on the beach is a random variable x. Y could be the random variable, how much ice cream, how many kids showed up on the beach. Now, each of them have their own distribution. Temperature, if you take enough temperature readings, they'll have their own distribution, enough information in there. And if you take how many kids show up on the beach, right, will have their own distribution. But you do realize that on warm days, on warm and pleasant days, more kids show up on the beach. Right? So suppose I give you the temperature. Temperature is fixed as a distribution of the temperature is fixed. Now, how many kids show up on the beach? There'll still be some uncertainty, but this is the definition of that. What is the uncertainty left in x after fixing y? With these definitions, we can then measure the mutual information between x and y, which is subtracting the information, like how many kids will show up on the beach, minus, now that you know temperature, what the temperature reality is, how many kids show up on the beach, what's the information, residual information or uncertainty in how many kids show up on the beach, right? So that is called the leftover information. This is the mutual information between these two quantities. In other words, you would realize that there's something shared. One has a dependence on the other. So the mutual information is essentially a measure of that. So they use these measures and then they continue on to do, there's some theorems and propositions, etc. And they define, important to note is that they use statistical measures. Remember, statistical measures are over the entire data sets. Unintended, the memorization part versus the generalization part. So they keep talking about unintended memorization. It is the thing from the data. Why is it unintended memorization? You don't train the model for it to memorize the data. That is the unintended effect or the undesired effect. And generalization is what you want. So you can actually quantify at the statistical level. This is the measure of memorization. This is the measure of generalization. But the problem with this is it's at the statistical level, right? But when you take one particular example of the data, not the whole of X, but one particular, a single data set, X is equal to this, we have a single training model then these definitions become hard, and they then delve into a whole theory of Kolmogorov complexity, which they admit is non-computable. Nevertheless, they have practical ways to work around it, and they define something called the Kolmogorov memorization. So they say that let theta be a reference model that approximates the true distribution of the data. Right? By reference model, you might almost take the perfect model or the ground truth model. In reality, what it means is that take a really big model, right, or other frontier model, and its understanding of the data, and let theta hat be the model trained on the data set. So whatever model that you're studying, smaller, much smaller model you're studying, let theta hat be that model trained on the same data set x1 to this. For each xi, that is for each instance of the data, we define, now notice that they're defining the memorization at the level of every instance of the data. How much of that data has been memorized? Right? And so, without going into too much of this, they point out that while it is true at the level of every instance of the data, when you aggregate over the entire data set, it becomes the same as the Shannon's entropy, which is an aggregate measure. Right? It becomes that. So we will skip that bit of uh, mathematics. And the way they do that, and again, a little bit of it, Kolmogorov with compression, they're basically saying that Kolmogorov's definition essentially boils down to what is the shortest compression or representation of that data point in bits that you can have, right? In view, so Kolmogorov, given this model, so given this data point, how many bits could you have represented it with? But now that you have a trained model, now how many bits can you represent it with? Which presumably will be smaller, right? In view of the model. So they go into all of that, but we'll take a flyover territory over this mathematical territory. But it is important to look at the results. They show that model capacity estimates across different widths and half precision. See, when you build a neural network, you can make it wide, you can make it deep, even with transformers. How many multi-heads that you want? How many layers of heads do you want? Attention heads do you want? All of those things together. So these are the layers. How many layers do you want to put in a feed forward? And so on and so forth. Then they find that no matter what you do, the model capacity remains approximately alpha. Alpha is the bits per parameter. What is the memorization? How much has it memorized? Remains the same. So when you take B float, by the way, B float is floating point. It is the most popular quantization that people like in machine learning. You train the models using FP, 32-bit precision, floating point precision, 32-bit. But the first quantization that you take, or smaller size memory that you take, is a B float. So irrespective of whether you take B float or you take FP32, the full precision, the ratios are not that different. And so from that, they conclude that double precision from B float to float 32 only increases model's capacity from 3.51 to 3.83. What does it mean? That B float is more than enough for it to capture most of its memorization. Only a little bit of capacity expansion happens if you take a bigger, more bits per parameter, right, to store. That's what they are saying, and that is pretty much the gist of it. Now, coming to more figures, training set and extraction rate. How much of the information can you extract from it? The more you increase the training set size, the less it will remember, because it can't. It has to start grokking it. It has to start generalizing from it, and so forth. And these curves, remember, likewise, you observe something very interesting in the second curve also. Extraction rate of a 64 token training sequence across prefix lengths for both training. But basic point is that it cannot remember. If you go on increasing training size, the model is forced to give up memorization. And when it gives up memorization, of course, you can't get back that information. Training set, membership inferences, basically asking the model, hey, have you seen this data? Right? And what will happen when it has memorized? You can say, you notice that its membership inference score is perfect because it has memorized at the top. But what happens as you increase the training data set size, it can't remember. It is forced to generalize. And so what happens is you see a drop, and it drops to 0.5. A 0.5 represents inference score. 0.5 means it's making random guesses. Right? It is not able to do that. And so if you plot membership inference, how often it gets the F1 score, how well it gets, you realize in the extraction rate that when the extraction rate is high, membership inference is high. It means like basically when it memorizes, both of them go together. This is it. So pretty much there's a bit of mathematics that goes with it, but that is the core of the paper. The most, I suppose, elegant part of this is, which is remarkable, that they their definition of memorization versus generalization, the mathematical expressions for them, must be really effective because it seems to align with all that we know about grokking, double dip, isn't it? And it seems to hold true across various scales of the data, various scales of the model parameters, right? With scales of the number of points of training and so on and so forth. And that, in a sense, is what this paper is about. So it just ties, in some sense, it gets into, or it contributes more to our understanding of all these things, double dip and grokking. And it shows that to it, it adds a body of knowledge. It says that if you go with the understanding that each parameter can store about 3.6 bits of data, then you can pretty much tell when grokking will take place. What is the practical utility of this paper? Practical utility is you better bring at least, you better exceed a model's capacity by a few orders of magnitude to make sure that it isn't memorizing, it's generalizing, to induce it to give up memorization and move more towards generalization. Right? And somewhere in there, if you look at what we do with modern LLMs, these days we take a typical, even an 8 billion parameter model, a 2 billion parameter model, 5 billion parameter, whatever it is, people are typically bringing 8 trillion parameters, a trillion tokens. When you bring that many tokens, you realize that you're far exceeding the model capacity. So any fear that you might have that the model is memorizing it, memorizing everything and answering everything from memorization, is probably unfounded. There will still be some residual memorization, but not as much as you would fear. Right? And this has been a talk. It's a thing that people always. So suppose I told you that every parameter can store as much as 1 megabyte of data, right? Suppose it were true. I don't know how that could possibly be true, conceivably, but nevertheless, let's say something like that was true. So then you could say, well, when I take a 1 trillion parameter model, right? It can pretty much memorize the whole world. It doesn't need to learn anything. And maybe that's what it is. Many people have suspected that these large language models, all they do is just memorize it, right? And interpolate from that. But I suppose this is an emerging body of papers that are coming out that more and more convincingly say that large language models are not just memorizing, right? They actually cannot memorize. You don't have the capacity to memorize. They have to generalize. And so it's adding to the body of evidence that these models are actually generalizing and learning from the data. Right? So what are the two axes, if you think about it? What are the two axes that induce grokking? One is bring enough data to overwhelm the capacity of the model. And the second that we know from the past paper readings that we did is that train for long enough, right? Because even with small data, you can induce grokking by just training for long enough number of steps, because that will induce grokking. But the sure shot way of inducing grokking that this paper mentions is train for long and bring lots of data. And then the machine will have to be grok. And I suppose that's a key message of this paper. Any questions, guys?
Yeah, I have a quick question, Asif. Is there, excluding financial and like any sort of geological problems, like in terms of energy and so on, is there a theoretical upper bound for this, or should there be none?
No, theoretical upper bound on how much a parameter can, upper bound to what? How much a parameter can memorize, or how much data can you train a model with?
Yes, yeah.
Oh, yeah. So the neural scaling laws say that you reach a point of diminishing returns. And in practice, what happens is when you bring lots of data, you will go through it at least a few epochs. But after a few epochs, you realize that you plateau off. See, the risk is the thing that people fear is, see, let's say that your loss has plateaued, right? How do you know that there is not another grokking movement after this, right? That you're stopping prematurely. And in some sense, this paper and many other similar things coming out conclusively show that so long as you have overwhelmed the capacity of the model, you need not fear, you can stop now. Right? There is not another grokking movement that will cause. So, in other words, if you have got, so what will happen is early on you'll go through, but you don't need to, there is no another grokking moment. Yeah, you have only one region of grokking. There isn't more and more regions of grokking lying in the future. So there's no point in training that further on. The other thing is, see, what does more data do? Our experience with more data is that more data always leads to better generalization. So, which is why, even though you train smaller models, you tend to bring more data because it brings diversity. Another way of saying it is that it makes it easier for the machine to detect patterns early on, right? So you overwhelm the capacity of the model, but it's beginning to generalize. But the more clear the pattern it can see, the quicker it will generalize, isn't it? And the general belief is that the more data you bring, the more clearly it can discern the pattern. So it's always a good idea to bring more data and perhaps run lesser epochs. I mean, after a certain number of steps, you know that you're done with it. Does that answer your question?
Yes.
Yes, just a question. So, does it mean that the smaller models will generalize earlier and better if it is given more data?
See, they generalize earlier because they get overwhelmed, but they don't generalize better because when there is large data, they can discover not only the gross features of the pattern, but also the nuances of the pattern in the data. Right?
Okay.
So bigger brains always lead to better generalization so long as you bring more data and more compute to it. That's a neural scaling.
Okay.
All right, guys. So, any other questions? I'd like to make an announcement. Tomorrow we are starting this course, this advanced RAG course. It's a RAG in depth, retrieval augmented generation in depth, and AI search course. It starts tomorrow evening. If it interests you, you're all welcome. Obviously, you're welcome to the first evening of the class. It is completely free. We have announced it on Meetup. If the topic of RAG interests you, I look forward to seeing you guys in that session. It's a 14-week course, 12 weeks of work and 2 weeks for still hardware access and TA access. We give you access to pretty good AI hardware, and we have 10 a teaching staff of 10 AI engineers who help you learn the topic. We cover advanced topics like semantic cache and fairly in-depth guardrails, model fine-tuning, and query expansion, agentic RAG, knowledge graph RAG, and knowledge graphs, and so on and so forth. So we go to the frontiers of research, but start easy and go pretty far in 3 months. And it's very practical, very industry based. If it interests you, please do show up tomorrow. Tomorrow is the first session. The first day of all our courses are always free. And for what it is worth, if you would humor me, I'll show you the course for that. It is somewhere here. Courses. If you go to courses, you'll see that there is a course. There we go. RAG and AI search. It starts tomorrow. Well, something is not quite right with my network. So